Okay, so thank you very much. Thank you to the organizers for the invitation. It's really a pleasure to be here. It's also an honor to be here. And I will give a short mini course on something which is, I will try to be very elementary because as you will see, I will do some very elementary arguments in order to deal with a very old question about connectedness on the space of group actions and diffeomorphisms. So, but before this, let me try to see if this works. Okay. It doesn't work? Okay. 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 So I will speak about group actions, and since we are in a conference on foliations, let me just recall something that we all know here, but it is worth to recall, that whenever you have a group action on some manifold, actually you can build a foliation, say a codimension one foliation, for instance, in the case of a group action on a one-dimensional manifold, by the procedure of suspension, and the transverse dynamics on this foliation by the holonomy is given by the dynamics of the group actions. So, for instance, if you take the dynamics of two commuting diffeomorphism, two commuting circle diffeomorphism, which is going to be the case in this series of lectures, then you can see the dynamics as the transverse dynamics of a codimension one foliation on the three torus. Okay, so very naively, let me simplify with this discussion by saying that in order to classify foliations, we should be able to classify group actions. This is not totally true, but okay, forgive me about this simplification. But this is a way to justify why my mini course will be about group actions and not directly concerning foliations. And I will mostly speak about commuting diffeomorphisms, although I will speak also about some more general group actions. And so let me give some definitions on the blackboard, because I would like to be clear on this. So for instance, that we have a manifold that in my case will be in general a compact manifold. And on this manifold we can define the space of diffeomorphisms, which is also a group. And if we take an element in the space of diffeomorphisms, say orientation preserving, in some cases homotopic to the identity, I will consider the centralizer of this diffeomorphism in most cases in the same regularity class, sometimes in higher or smaller regularity class, which is the set of diffeomorphisms. So I will allow to change the differentiability class here. So this is the set of diffeomorphisms that commute with the given F. So this is a subspace of the space of diffeomorphisms, and given F, studying the structure of this space is a very important problem in dynamics, and there is a lot of work on this. I think starting from the thesis of Nancy Koppel in the 60s, and there are many, many works on this, so I didn't put all the references concerning this here, but I wanted to refer to the work of Bonatti, Crovisi, and Wilkinson for the case of C1 diffeomorphism, which is very nice, and I think it contains most of the relevant literature, at least up to that paper. And they show that generically, so for a generic C1 diffeomorphism of a manifold, of a compact manifold, this space here, the centralizer, the C1 centralizer, is trivial. Triviality means here that it is not that it is the empty set, because the centralizers, at least in the same differentiability class, always contains the set of powers of the given diffeomorphism. And it turns out that in most of the cases, in a generic sense, these are all the diffeomorphisms that commute with the given diffeomorphism. Okay? So this is a kind of mental picture that I have on this. Maybe this is very naive, but I like to draw this picture. So for me, so given a manifold, I will put here the space of diffeomorphism of the manifold of a given regularity, and here also the space of diffeomorphism of the manifold, and a pathological diffeomorphism like this, which is actually a genetic diffeomorphism, is a diffeomorphism F for which the only diffeomorphism that commute with F are the powers of F, something like this. So this is somehow the identity, this is F to the square, and so on. Again, this is a simplification, and this is just a mental picture that I have. And there are other diffeomorphisms for which this centralizer is much bigger. For instance, if you have a vector field on the manifold, and this diffeomorphism arises from a vector field, then you have the whole flow of the vector field inside the space of commuting diffeomorphism. So there are some other diffeomorphisms for here for which there is some one-dimensional stuff here. Okay? But this is not the generic case, actually, because of this theorem. Actually, this was proved by, I think, by Jacob Pallis for the first time, but in higher regularity, no, in C infinite, that a generic diffeomorphism doesn't arise from a vector field, for instance. Well, this result contains this statement. And the question that I would like to address in this mini course is, for instance, if I take a pair of commuting diffeomorphisms here, F1, G1, and another pair of commuting diffeomorphisms here, F2, G2, I would like to find a path between these two pairs of commuting diffeomorphisms that goes through commuting diffeomorphisms. Okay? So it goes through this, for instance, this particular point here, something like this, and it has to cross only commuting diffeomorphisms and to move in this subspace in a continuous way. Okay, this is a totally natural question, and it turns out it is very difficult to answer. So we would like to say, yes, of course, it is possible. But I will try to explain you, especially today, that the naive approaches to this question actually fail. And I will try to convince you that this is, at the same time, difficult and interesting. And this is even interesting in the case of a manifold M of dimension 1. I will concentrate in this mini course in the case of one-dimensional manifold, compact one-dimensional manifolds, which means the circle or the closed interval. And even in that case, the answer to this question is unknown in general. Of course, the question depends also on the differentiability class. And I will also show you that this is very important to consider and to keep in mind, especially when we go into computations. But let me give another motivation. There are at least two relevant motivations for this question, besides the fact that it is a natural question. So there is a question by Harold Rosenberg, I think in the 80s, or mostly, or maybe in the 70s actually, about the case of commuting circle diffeomorphisms. So this was inspired by the thesis of Michel Herman concerning linearization of circle diffeomorphisms. And the question is whether the space of commuting circle diffeomorphisms is locally path connected. So this is still open. So the regularity class is not explicit here, but he was thinking about the case of C-infinite circle diffeomorphisms. And I think that even in the real analytic case, this is still open. Okay, this was treated by Yokos. At some moment, Yokos thought he had approved, but he didn't write it. Right, this is still open. And the result that I would like to, yes?
I think that the question of Rosenberg is to ask if there is pair of commuting diffeomorphisms on the circle which are structurally stable.
Yeah.
That is around the unique commuting diffeomorphisms are conjugated to the circle.
Exactly, exactly. Yeah, this is a rephrasing of original Rosenberg question. It's not exactly equivalent. There are a lot of discussion of this on this because So I met Harold Rosenberg some months ago, and we discussed about it. He forgot a little bit on it. so he didn't.
This very question, I remember reading it in a paper by Rosenberg.
This is explicitly written in the volume of Asterix by Yokos. Yes. Mm-hmm. Yes. Thank you. And the theorem that I would like to discuss here is a theorem that we proved with Hélène Eynard concerning a very particular differentiability class. So we were able to prove that the space of C1 plus AC commuting diffeomorphism of the circle is path connected. So here I need to introduce what is AC. Okay. So this is almost C2. And you know C2 in one-dimensional dynamics is very important because it's the differentiability class you need for Danjois theorem. But actually, this is not C2. And actually, Danjois theorem works in regularity classes which are slightly smaller. So let me remind something. So I will denote this by C1 plus bounded variation. This is the Danjois class, which means that the derivative, so an f is here if the derivative has bounded variation. Okay, and in order to do computation, it's better to look at the logarithm of the derivative, but actually this is equivalent. So we are assuming that the diffeomorphism is C1, but the variation is bounded. Okay? Now, C1 plus absolutely continuous it is actually a group. It's the subspace of those diffeomorphisms for which there is a second derivative, but in L1. Okay? So if you wish, the space C1 plus absolutely continuous, so F is here if, well, it is in the Danjois class, and the logarithm of the derivative, or the derivative, which is absolutely continuous. This is equivalent to the fact that the second derivative is in L1. Okay? And actually, well, it is better, again, it is better to look at instead of looking at the derivative here, to take the logarithm of the derivative and to take the derivative of the logarithm of the derivative. So this is equivalent to the fact that the second derivative over the first derivative of f is in L1. And this is the version that I will keep in mind because this is very useful. And the reason is that this thing here, which is the affine derivative, has a chain rule. And this will be very important for doing computations. So I will come back to this, I think, in my last talk. And, well, in case this is a continuous function, this is the space of C2 diffeomorphisms. So we are able to prove path connectedness in this particular space. we don't know how to prove even connectedness, I think, in the Danjois class. And this is very interesting because this is related to the work of John Mather. Yes, you have a question?
So you said that it's weaker than second, twice differentiable.
Yeah.
But you write that expression saying it's in L1. What
Yes.
do you mean by that? So what does D2 of F mean here?
This is almost everywhere, the final and the integral of. So this is a nice exercise in order to relate C1 plus bounded variation with C1 plus AC. So if F is in C1 plus AC, then the variation of the logarithm of the derivative can be computed by an integral. This is the integral of the absolute value of the derivative with respect to the Lebesgue measure. So this is because it is absolutely continuous. So this is one of the possible definitions of absolute continuity. But this is what? This is the D2 over D. Okay? So this is the L1 norm, if you wish, of the affine derivative. Okay? And from this point of view, if you take Danjois, this is, I will call it the Danjois inequality, but this is the fact that, which is crucial in the proof of Danjois theorem, that the variation of the logarithm of the derivative of the composition is smaller or equal than the sum of the variations. This becomes the triangular inequality in L1, okay? Because, you know, you have the second derivative. This is the chain rule for the second derivative, for the affine derivative. This is what? This is the affine derivative of G plus the affine derivative of F composed with G multiplied by the derivative of G. And if you integrate this, you take the L1 norm, because of this change of variable here, what you get is exactly this. Okay, and this point of view is allows to, instead of dealing with variations and so on, you get into some very nice Banach space, and you can do some, say, linear interpolations and things like that. So everything becomes easier. Okay, but the point is that we don't know how to prove connectedness in the Danjois class. And we also don't know how to prove path connectedness in C2 differentiability, but for that case, we prove connectedness. Okay, so let me describe some previous results on this. Let me start with something very elementary. So the case of homeomorphisms. This is already very interesting. So if you take actions by homeomorphism of the interval, then this space is path connected, independently of the group which is acting. This is because of the Alexander trick. But it only works for the interval. So the Alexander trick consists, well, if you have an action on the whole interval, then you conjugate so that you see this action as an action as a smaller and smaller interval, and you complete the action by the identity outside. And in the end, you get something which is trivial. So you are able to connect any given group action to the trivial action. And this way, you can connect any two given actions. Of course, there is a problem with differentiability with this construction, but it works. It's very, very elementary. But if you go to the case of the circle, things are much more complicated. So it is far from being true that the space of any given of actions of any given group is even connected. So for instance, there is this wonderful paper by Catherine Mann concerning the pi1 of surfaces. But this is still true for abelian group actions. And there is a very nice argument in the thesis of Michel Herman that gives this, and I will go into the precise computation. So given any two commuting, pair of commuting homeomorphisms of the circle, you can connect them by a path. Now, if you go to C1 differentiability, there are some results. For instance, following somehow a variation of the idea of Michel-Hermann that I will describe, it is possible to prove that the space of commuting C1 diffeomorphism of a one manifold is path connected. And what is interesting here is that this is also true for the case of small groups in a certain sense. So this is also true for the case of nilpotent group actions and there are some points here. So there are many proofs for this. For instance, so I proved this using a variation of Hermann's idea, but this was proved independently by Kieran Park by a very direct computations. There are approaches which are independent by Eglantin Farinelli, Bonatti and Farinelli, Gelman and Bonatti, and so on. So this is more or less well understood, at least for the case of commuting diffeomorphisms. And the interest here, besides even the case of commuting diffeomorphism, is that there are many examples of group actions in this C1 regularity. And this comes from, for instance, from the case of Danjois for the case of the circle. And for the case of the interval by Dennis Pixton and Takashi Suboi, who build a very large variety of actions of abelian groups on the interval, Farb and Franks and Jorquera for the case of nilpotent groups, and so on. So for instance, let me illustrate this by the following thing. So using Danjois method, it is not very difficult to build two commuting Danjois counterexamples on the circle. And it is not evident how to connect such a pair of commuting diffeomorphisms, for instance, with a pair of rotations. Okay. So this is contained in this theorem. On the other hand, there is a kind of criticism here because we are dealing with the case of C1 diffeomorphism in C1 regularity. Well, there is a lot of flexibility. There are a lot of actions, and maybe it is easier to connect to given actions because there are a lot of actions, which are actually impossible in higher regularity, because, for instance, of Danjois theorem. Okay, now I will benefit of the fact that three of the authors of this paper, Mate, Bon, Triestino, and Kim, are here, hopefully, yeah. And I think that there is a very nice recent paper by them concerning groups of sub-exponential growth, so which is something between nilpotent groups and solvable groups. And they were able to prove that any given action actually can be realized as a C1 action, which is very close to the trivial action in a certain sense, in C1 topology. And well, first of all, these actions are relevant because there are groups like this. There are kind of variation of the classical Grigoriev group of intermediate growth that acts on the interval. And I think you proved this. I think it is not stated in your paper. I think you proved this. Can you confirm this? That the space of groups of the space of C1 action of a group of sub-exponential growth on the interval is C1 path connected. I think it follows from your theorem. Almost. Almost. Maybe, I think. So what the difference for the previous case is that in the previous case, for the case of abelian group actions and nilpotent group actions, the connection is given by conjugacies, by topological conjugacies. And in the case of this recent paper, the connection should be by topological semi-conjugacies, okay? And when I was preparing these talks, I realized that I think that this question is still open for the case of solvable group actions. Okay, I think there have been many progress on the study of solvable group actions by C1 diffeomorphisms, particularly by Gelman and Lewis. It's a paper together with Christian and Nacho Monteverde and Cristobal Rivas, and there is another paper by Brum, Matebon, Rivas, and Triestino that gives a structured result for C1 actions of solvable groups on the interval. And I think that if C1 connectedness is true, one should be able to prove this nowadays. Maybe, I don't know. This is why I state this as a question. But let me emphasize that this is not true in general. So for the case of continuous action, because of Alexander trick, independently of the group, the space of action is connected, is path connected. But for the case of C1 actions, this is not true. This follows, for instance, from a remarkable paper, say, it's mostly a book, actually, by Brum, Matébon, Rivas, and Triestino. Okay, let me explain a little bit on this. So, because the example is very nice, it concerns the Thompson's group F. What is it? Okay. So I think everybody here knows Thompson's group. Okay, so I will start with Thompson's group F. So this is the one that acts on the interval. And there is a construction by Thurston and a variation of this construction by, no, this is actually a generalization by Gis and Sergescu that says the following. Actually, F embeds into the group of C infinite diffeomorphism of the interval. So in the original definition, F is only a group of piecewise affine homeomorphism of the circle, of the interval. And there is a realization by Thurston, which is C1, actually it is almost C2, it's C1 plus Lipschitz. This is the piecewise projective realization, and there is a variation of this, which is a very large extension by Gis and Sergescu, that shows that F actually embeds into the group of C infinite diffeomorphism of the interval. One cannot put here real analytic because of several reasons, but one can go to any given differentiability class. So F is a group of C1 diffeomorphism of the interval, which is not trivial. It's not evident because of the breakpoint, but there is a procedure to kill these breakpoints in a certain sense. And the point is that these actions are somehow rigid. So these guys here, Brum, Matébon, Rivas, and Triestino, prove, among many other things, that one can somehow classify the actions of Thompson's group F. This was discussed by Michele in the previous talk. So there is this canonical action up to topological conjugacy, and there are many, many other group actions. They are able to prove that the only C1 action is the canonical one. Okay? Of course, there are many other actions, but which are smooth, but those actions are not faithful. So because you can take the derivative at the endpoints, and this way you produce a homomorphism into the C to the square, whose kernel is the commutator subgroup of F. And the point is that it is impossible to connect for instance, the G-Sergescu action with such an action. Okay, to connect them by a path of C1 actions. Okay, so again, this is not explicitly written in the paper of those guys, but it follows from that. Okay, so in general, the space of C1 group action is not path connected on the interval. And in higher regularity, there is another very nice result by Christian and Hélène concerning the C-infinite differentiability class. So in that case, and again for the interval. So So there is a preprint by Avila and Krikorian that should prove that this is still true for the case of circle diffeomorphism, but I am not totally sure. But this is a theorem by Christian Hélène that says that the space of C-infinite diffeomorphism of the interval, commuting C-infinite diffeomorphism of the interval is connected. But we still don't know whether it is path connected or not. Okay? There is a deep problem which appears in the proof. And the relevance of path connectedness here comes from the thesis of Hélène again. So she proved in her thesis that if the space of commuting C-infinite diffeomorphism of the interval is path connected, not only connected but path connected, then one would be able to connect any two given codimension 1 foliations on a compact 3 manifold for which the tangent plane fields are in the same homotopy class. Okay? So this is another instance of relevance of this question about path connectedness of the space of commuting diffeomorphisms. And of course, if you want the details of this, you should ask Hélène, because the proof is really very involved and it's very nice, but I am not aware of the details of this. And as I mentioned before, so again, we were able to prove using our method that the space of, at least of the space of C2 diffeomorphism, commuting C2 diffeomorphism of the interval is connected, but again, we lack of path connectedness here. Okay, and now I will try to explain why it is difficult to deal with these problems. And I will try to illustrate why the naive approaches to these problems actually fail. Okay? This is my goal today. Okay, the first thing is, as I mentioned before, is you play the Alexander trick. It doesn't work in any regularity. Okay? Another trick we would like to use is to deform diffeomorphism just by deforming the graph. Okay? So if you are dealing at least with diffeomorphism of the interval, so in general a map on the interval is just a graph. Okay? Something like this. Okay. And we would like to do the naive approach of following the linear isotopy of the graph of the given map F to the diagonal. Okay? Actually, this works for a single homeomorphism. But if you have two commuting maps and you perform this procedure along the path, you don't get a homeomorphism that commute. This is the problem with this. Okay? So this idea doesn't work. Now, if you try to use some deeper results concerning linearization for the case of the circle, well, not so deep. So even the most elementary ones, you take C2 diffeomorphism of the circle, and you know from Danjois' theorem that actually up to change of coordinates, this is a rotation. And if you take two commuting circle diffeomorphism of class at least C2, actually they are simultaneously conjugate to rotations. So up to change of coordinates, what you need to connect is a pair of rotations, two pairs of rotations. But the problem here, of course, is the fact that the change of coordinates, the linearization in general is not smooth. So when you try to perform this connection, you will leave the space of diffeomorphisms. So it doesn't work. Okay, this is kind of motivation to extend this question for the interval to the case of the circle, but it doesn't work. Now, if you go to the case of the interval, where things seem to be easier, there is something which is very nice, actually. So for the case of the interval, Sequeres proved in the 60s, I think, that this case is very different to the case of the circle. So a circle diffeomorphism in general doesn't arise from a vector field, but for the half-closed interval, every diffeomorphism, at least with no fixed point and interior, actually comes from a vector field. Okay, this is what is called the Sequeres vector field. And actually, the work of Nancy Koppel classifies the situation for two commuting maps. So if you have two commuting diffeomorphisms of the interval, it is known that they are associated to the same vector field. The problem with this is that the vector field in general is only C1. And this is actually the generic case. This was proved by Sir Gerard in the 70s. And this was illustrated with a very classical example of a diffeomorphism of the interval for which there is no C2 square root. The square root is only C1, is the time 1/2 map of the vector field, but this map is only C1 and it's not C2. Okay? And actually the situation can be much more complicated. So you can have a diffeomorphism of the interval for which sometimes are smooth, by this I mean C2, and sometimes are not smooth, and the space of times for which it is C2 smooth is very complicated. It contains two irrational independent numbers, and it's the set generated by these numbers and so on. So there are very nice work by Hélène again, and Christian and Hélène concerning this. So it is not a good idea to deform commuting diffeomorphism of the interval following the Sequeres vector field, again, because you may lose the regularity along the path. Okay? So this is the naive approach. It doesn't work. And there is still another pitfall, because in the previous slide I only deal with diffeomorphism of the half-closed interval. And here, if you close the interval on both sides, then a Sequeres theorem produces two vector fields, one on the left and one on the right. And it turns out that these vector fields actually in general are different. Okay? And again, this is the generic case. Okay? This was clarified by your mother. And again, it is there is a chapter in the thesis of Jean-Christophe Yocos concerning this difference of the two vector fields. This is captured by something which is called the Mathers invariant. I will speak about this on my last talk. And there is an analogous construction in the setting of complex dynamics, of parabolic maps, parabolic gems of complex diffeomorphisms by Voronin and Ekal. But I put it in red here because this is going to be very important. There is some structure on this. And John Mather proved, for instance, if these two vector fields are different, then the centralizer of the diffeomorphism is infinite cyclic. Okay? Maybe it is not reduced to the powers of the diffeomorphism. Maybe it is not trivial, but it is generated by a single element. Okay? And this is going to be crucial in the end of the proof of the path connectedness of the space of commuting diffeomorphisms. And any question? No? And the idea to prove this connectedness resulting in lower differentiability, mainly C1 and C2, is a very simple idea. Instead of following the vector fields and the flows, which may fail to be smooth, there is something very naive that one could try to implement, is try to follow the conjugate actions. Okay? You start with two commuting maps and you try to conjugate them by a diffeomorphism so that in the end you get the other pair of commuting maps. Okay? So this is so. A very simple idea, and the inspiration comes from, for instance, in the group of Möbius transformation, a parabolic element is an element which is conjugate to the roots, for instance, to the parabolic flow. And we would like to do the same for commuting diffeomorphisms. And the reason for doing that is that we get for free the commuting condition along the path, because we are conjugating commuting diffeomorphisms. So this is a nice exercise. Okay, if you take a circle homeomorphism, then it contains the corresponding rotation in the closure of its conjugacy class. Okay, and this is explicitly written in the thesis of Michel Herman. So and this is the starting point of this. So there is a chapter in the thesis of Michel Herman which is called how to conjugate a given diffeomorphism to a diffeomorphism which is close to a rotation. Okay, because in the proof of the linearization, the thing that he was able to do at that time is to prove the general linearization theorem by using the local linearization theorem. And for that, what he needed to do was to start with a given diffeomorphism and to conjugate so that it becomes closer and closer to the corresponding rotation in the good topology. Okay? Okay, and the picture is this. So I start with a homeomorphism of the circle. So and I can take a leaf, and I will do something very simple with the leaf. I will consider this map Hn tilde is going to be 1 over n, the Birkhoff sum along the orbit. Okay? So this is a continuous map. This is increasing, and this commutes with the translation by 1. So this induces a homeomorphism of the circle. Okay? And there is this computation in the thesis of Herman again. So if I take the value of h at the image point, I will get more or less the same. I will get 1 over n, the sum, but of f tilde I plus 1, which is almost the same, except for the first and the last term. So this is the Birkhoff trick. So if I take the difference here, this is 1 over n, I think f tilde to the power n of x minus x. Okay? And this, because of the definition, if you wish, this goes to the translation number of f tilde. Okay? So if we go back to the circle, we are proving that Hn composed with f. No, I will keep on the real line. So Hn composed with f and minus Hn goes to the translation by this translation number. Okay, and which means that if you compose with the inverse of Hn, for the case of the circle, this goes to the rotation by the rotation number of in C0 topology. Okay? And now the point is that this very naive idea actually works in dimension 1 for commuting maps. Okay? But before that, let me discuss the higher dimensional case. So for instance, for the two torus, there is a theorem essentially proved by Quapix, but not stated that way. It is stated this way in a paper by Began, Croviciel, Juan Patou, that the same is true for the case of homeomorphism of the torus, for which the rotation number is a single point, which is totally irrational, for instance. And this requires a lot of work, actually. It doesn't work like this with a formula and so on. It really requires some combinatorics of the map. So again, the point is that this very naive argument actually works for two commuting homeomorphisms of the circle. If you start with two commuting homeomorphisms of the circle, it is very easy to produce a path of conjugate of this action that ends with an action by rotations. Okay? So this is the conjugate here. It's the same formula but incorporating the two maps. Okay? So this is the Birkhoff sum along the, say, the square, the positive side of the ball of radius n in the abelian group generated by these two maps f and g. And if you do the exercise and you compute the conjugate of f and g by this h equal to hn, what you get is something which is close to that formula. So you will get something which is very close to the rotation simultaneously for f and g. So starting with any given commuting circle homeomorphism, you can connect them with the corresponding rotations. And of course, the rotation that will appear will be the rotation by the rotation number. Okay? So here is the computation. So I will give a copy of this slide if you wish. So because this computation is very large. So the point is that, well, it doesn't work. Okay. I don't know why. Now it's working. Okay, so I have to replace x by f tilde of x. And the only point that I need to use here, I will show the key point here, is that I can commute f with g here. This is the only thing. And that way, I can go ahead and do the Birkhoff sum trick. And now I will get this formula here. hn of f minus hn is 1 over n, this sum. But for every given j, this is going to the rotation number of f, to the translation number of f tilde. But here I am taking 1 over n some mean. So this part of so this expression here is converging to the translation number of f tilde. And the same holds for g. So it works. And actually, the argument is so explicit that it shows that the space of commuting circle homeomorphism retracts into the product S1 times S1, because everything is explicit. Actually, this was a remark by Alberto Berchowski when I was giving a lecture on this.
I just have a quick question. So, is it very clear that hn tilde is even homeomorphism?
Thank you. Yes, because this is, okay, let me go back to the definition. So this is hn tilde. So it is continuous, it is increasing, and it commutes with the translation by 1. So it induces a homeomorphism of the circle. Thank you. Okay? And again, when I was preparing this talk, I realized that the proof of connectedness of path connectedness of the space of C1 commuting diffeomorphism of the circle doesn't give this retract. So there is a problem for when dealing with C1 diffeomorphisms. And there is something which is evident. So we cannot play this game for C1 diffeomorphisms because of the eventual existence of hyperbolic fixed points. If you have a hyperbolic fixed point and you start conjugating the action, you will never kill the multiplier of the fixed point. So you will never get close to a rotation in C1 topology, or close to the identity for the case of a fixed point. So there is something that needs to be done here. So this is the reason why the proof that I will somehow sketch doesn't give this retract for the case of C1 actions. Okay, but let me go to the case of C1 diffeomorphism, because this is still very, very elementary from this point of view. So this is a fact. And I have to apologize because I remember I have seen a paper on this in the 90s, but I forgot the name of the author. But I know this was in the literature in the 90s, at least for the Danjois example. So every C1 diffeomorphism of irrational rotation number of the circle contains the corresponding rotation in the closure of C1 conjugacy class. Okay, which is not obvious. So there is a procedure, if you start with a Danjois counterexample, any Danjois counterexample, there is a procedure to kill the wandering intervals along the path and get in the end the corresponding rotation. Okay? And the proof, as I remember, is a very technical proof by hand. I mean, you look at the length of the intervals and you try to decrease the length of the intervals and so on. You compute derivatives and so on. But here there is a proof which is much simpler, using the very same idea. The idea is taking means. But the point is that the formula that I gave before, even for a single map, doesn't work that well. If you take the derivative of this map, this becomes awful because of the composition here. It is better, instead of taking the mean of the map, to take the mean of the derivative, or even better, the log of the derivative. So this is the formula for the case we are dealing with C1 commuting diffeomorphisms. So I take two diffeomorphisms of the circle, F and G, that commute, and I produce this map here. And it's a kind of miracle of algebra that this works. Okay? So I know what is your question. So is it clear that this is a circle diffeomorphism? Okay. Okay. So this is just a formula. I prescribe the derivative of the map. I am prescribing the derivative of H. Log D, sorry, log D. Yeah. Okay, now I understand your question. Yeah, log D, sorry, log DHN. So there is this formula here, and we had to add some constant in order to make it a circle diffeomorphism, so to make it a map of total integral equal to 1. So this is actually very explicit. So let me transform this into a formula for the case of a single map. For the case of a single map, I have to add this constant because otherwise the total integral of the derivative could be different from 1, and I want a total integral equal to 1. So for the case of a single map, the Hn of x will be something like the integral between 0 and x, the nth root of the product of the derivatives up to time n minus 1 divided by the total integral of this. Okay? And the constant Cn would correspond to the logarithm of this term. Okay? And this works because of this computation. Okay, this is a kind of miracle, but I will not go into the details here, but the point here is that the logarithm of the derivative is much better behaved than just the derivative. The logarithm of the derivative satisfies the chain rule, the logarithmic chain rule. And this is what is behind it. But there is a problem. The problem is that in the end, remember that in the previous case there was the rotation number that was appearing. And here there is this, the derivative of f, the logarithm of the derivative of f to the power n divided by n. And this, when n goes to infinite, converts to the Lyapunov exponent. So everything works well if the Lyapunov exponent vanishes. And it turns out that, for instance, for the Danjois examples, it vanishes. So in dimension 1, if you have a non-trivial Lyapunov exponent, it is because you have a hyperbolic periodic point. So if you have no hyperbolic periodic point, you can play in this game for commuting diffeomorphisms, and actually some variation actually works also for nilpotent group actions. But in case where there is some periodic hyperbolic periodic points, something is missing, okay? And just to summarize, I will just say that. So finally, the idea is to do some affine interpolation like this. But instead of playing with the graph of the maps, I will play with the logarithm of the derivative, and I will do the affine interpolation in the space of continuous functions, the space of the derivatives. And the key point is that the logarithm of the derivative are cocycles, so the algebraic part actually works. And the only problem is hyperbolic fixed point. So I will start tomorrow by explaining what to do when there is a hyperbolic fixed point, how to kill them somehow. And in that way to get connectedness of any given commuting diffeomorphisms. Okay, thank you.
Thank you, Andres. Are there any questions? Yes.
So this kind of argument that's over there, and it seems it's really connected to the fact that balls are Follner sets. Does it, for instance, just in C0, is it true for all amenable groups?
So the proof actually, no, you need more than that. You need more geometry. It works for nilpotent groups.
For nilpotent, yeah.
But it doesn't work this because, you know, there is some cohomology there. So what is happening here is this algebraic miracle is because there is a very general lemma on cohomology for representation of groups on Banach spaces. And that lemma doesn't work for suburb groups, okay? And I wonder whether it is true for groups of sub-exponential growth, actually. I don't know. It's a question that I have. But this idea of using these maps is classical, and I discovered it reading a paper on cohomology of group by Didier Pinchon and Olagné. It's a very old paper where they were dealing with the cohomology of nilpotent group actions. And in that paper, there is a counterexample for the general statement for suburb groups.
Yes, Sam.
This is a naive question. For the case of homeo, that you actually said that the homotopy type is S1 times S1. Is it also true when you have more than two commuting?
Yeah. So during my lecture, I will only concentrate for the case of two commuting maps, but it's the same if you have many commuting maps.
It's interesting because it's also true for finite dimensional Lie groups that it's the same homotopy type as the commuting elements for the maximal compact, and the maximal compact for homeo is S1.
Yeah.
And that was interesting.
I agree. Yeah.
Other questions? Yeah.
Some random questions. So given a diffeomorphism, does it make sense to consider the largest regularity in the non-trivial as a non-trivial centralizer? So given F, so what is the largest R such that some G of CR, which is non-trivial and commutes with F?
Yeah, it's a natural definition. I see no. What do you think, Christian? You can do. So the centralizer will change if you change the regularity class. The diffeomorphism is fixed, I think, yes? And you change the regularity. So you get spaces that decrease as you increase the regularity.
You wonder about the first regularity where the centralizer
Is non-trivial.
What I mean is that you can later.
Maybe.
Other questions? If not, let's thank Andres again.